everyone, this is Mr. Bailey picking up on explaining the concepts of exponential functions. So prior to this, you guys just worked in groups on our bouncing ball problem. So this is where each group either had a tennis ball or a ping pong ball. You guys are dropping it from 6 feet and trying to figure out how high it bounced each time. So if it was 6 feet, the next bounce is probably going to be about 3 feet. We will get to why that happened later on. So you guys made tables and graphs to help represent that. Now let's dive deeper into that and we'll come back to those later on. So first let's backtrack first. Let's do a quick reminder on linear functions and quadratic functions. So we have two linear functions here, y equals 2x and y equals negative 5x. This is represented by our red line and our blue line. So these have a constant slope. Our y equals 2x has a slope of 2. And our y equals negative 5x has a slope of negative 5. And then our quadratic functions, y equals x squared and y equals negative x squared plus 3x minus 4. The second quadratic function is written in our ax squared plus bx plus c format, which we worked on previously in lessons using our quadratic formula and graphing those types of functions. So our y equals x squared is our green line focused at the origin, and our fourth one, y equals negative x squared plus 3x minus 4, is this purple one down in the corner. The reason that one's not focused at the origin compared to the other three lines is due to that 3x minus 4 that shifts that parabola down, and that's facing downward because it's negative. Now how would we figure out how to graph these if we didn't have access to a graphing calculator or other technology that'll graph it for us? The easiest way to do that is to make a table. So for our f of x equals 2x or y equals 2x, we could choose 5 different x's. For myself, I did negative 2 to 2. So if we plug in negative 2 for x, we get negative 4 for y. We plug in negative 1 for x, we get negative 2 for y, 0 for x, 0 for y, 1 for x, 2 for y, 2 for x, 4 for y. And this is just simply plugging this into our equation. 2 times negative 2 is negative 4. 2 times negative 1 is negative 2. So on and so forth. Similar process for our negative 5x formula. This one, our y values will go by 10. So it'll be 10, 5, 0, negative 5, and negative 10 for those same respective x's. The reason this one goes down is because of that negative sign in front of the 5. That means it's going to have a downward or negative slope. Now for our quadratic functions, for our first one, I chose our same 5 x's to plug in. So negative 2 squared gives us 4, negative 1 squared gives us 1, 0 squared gives us 0, 1 squared gives us 1, and 2 squared gives us 4. We could plot these points on our graph and then graph a best line of fit onto those points. Now for our fourth equation, I chose a few extra points. So I still started at negative 2, but I got to 2, and I realized that both values of x of 1 and 2 had y values of negative 2. So up to this point, I had like this little fishhook kind of curve. I didn't quite know how to picture the rest of it, so I went ahead and added 3 and 4 as x values to our table. And this gave us y values of negative 4 and negative 8 in addition to the rest of these. And that helped me better graph the rest of this photo. So this is a good reminder that even if certain x values work for other equations, we might have to add other x values or choose different x values altogether to get a better picture of different equations. Now, let's introduce our new function, an exponential function. Exponential functions are functions that have a variable in the exponent. So these are things such as y equals 2 to the power of x and y equals 1/2 to the power of x. Now just because I chose 2 and 1/2 as our base does not mean these are the only exponential functions. These are just happen to be two numbers that I chose to put as our base. The key to it being an exponential function is that power to an x. Now compare these to the 4 previous equations, both linear and quadratic, that we looked at. Some of these functions, the quadratic ones, do have exponents, but they have integers in the exponents. not variables. And our linear equations, they don't have any exponent visible. Now they do both have a power to the 1, but we don't really ever have to worry about that. If we just see an x, we know it's a linear function. If we see an x squared, we know it's a quadratic function. And if we see a power to the x, we know that's our new function, an exponential function. So let's practice really quick. Go ahead and pause this and try and figure out if these equations are linear, quadratic, or exponential. So for our first one, we have y equals 3 to the power of x. Our second one, we have y equals 10 minus x to the power of 2, or x squared. We have y equals 3x minus 5, and y equals 1/3 to the power of x. Go ahead and try and figure out if these are linear, quadratic, or exponential. So let's go over these and figure out y. So y equals 3 to the power of x is exponential. This is once again because of that power to an x, or power of x. Anytime we have a base that's a number to the power of a variable, you know that's going to be an exponential function. Y equals 10 minus x squared is quadratic. This is because of that x to the power of 2. Anytime you have x to the power of 2, it's going to be a quadratic equation if that's your largest power. Y equals 3x minus 5 is linear. This is because our only x doesn't have an exponent with it that's visible. And y equals 1/3 to the power of x is exponential. Same as the first one, because we have that power of x, we know it's an exponential function. Now how can we best represent exponential functions? Here I went ahead and graphed our first two. Y equals 2 to the power of x, and y equals 1/2 to the power of x. What do we notice about between these two graphs and tables? So for 2 to the x, we start really slow and then increase very quickly. And for our 1/2 to the power of x, we come down very quickly and start to gravel out. And looking at our tables, if we plugged in x equals -2 to our 2x equation, we have 0.25 or 1/4. -1 for the x, we get 1/2 or 0.5. 0 for the x, we have 1. 1 for the x, we get 2. And 2 to the x, we get 4. This is because 2 squared is 4, and 2 to the power of 1 is 2. Now for our 1/2, we have these same y values, but going the opposite direction. So for -2, we get 4. For -1, we get 2. For 0, we get 1. For 1, we get 0.5 or 1/2. For 2, we get 1/4. Now, there's a couple key points that I want us to figure out about these graphs. So, our first one is increasing. And this is because our base, that's our 2, is greater than 1. So anytime your base that has that power of x with it is greater than 1, it's going to be increasing. For our second graph, we have 1/2. That's between 0 and 1. That one's going to decrease because that base, the part that has that power to the x, is less than 1 but greater than 0. Another key point is because these are only equations with that power to the x, not anything accurate such as a +1, +2, they always cross at y equals 1. So even though they are two different graphs, one increasing and one decreasing, they both share that y equals 1 point. Now let's practice. Go ahead and make a table and graph y equals 3 to the power of x. Once again, go ahead and pause this video and try and fill out this table that I made and go ahead and graph it on the graph. And I'll be back with you shortly. So let's take a look at this. So for our table, we get -2 for our x. This we get 1/9. Why is this? So if we put this into our equation, we have y equals 3 to the power of -2, which flips, so it's 1/3 squared, which gives us 1/9. For x equals -1, similar process, we get 3 to the -1, which we flip, so 1/3. X equals 0, any base to the power of 0 is always 1. X equals 1, 3 to the first is 3, and x equals 2, 3 squared is 9. And this looks like this graph up here. So it's similar to that 2 to the x graph, but it increases at a faster rate. And we'll get to that in a moment. So why do we need this? Like, when are we going to use this in life? That's always a very important question to ask. Our ball drop experiment is a decreasing exponential function. So similar to that 1/2 to the power of x that we looked at. This we can best visualize by drawing a line of best fits on the graphs that we made. So go ahead and draw a line connecting the points on the graphs of your ball dropping graph. So each time the ball bounces, the height of the ball reaches is approximately 1/2 of the previous height. So the first drop was at 6 feet. So after that first bounce, it probably reached about 3 feet. After that second bounce, it probably reached about 1.5 feet. After that third bounce, probably about 0.75 feet, so on and so forth. So what do we notice about this? We can figure out that exponential functions have a rate of change of a constant multiple. Now this is different than linear and quadratic functions. So in the case of our ball drop, that constant multiple is 1/2. So 6 times 1/2 is 3. 3 times 1/2 is 1.5, or 3/2. 3/2 times 1/2 gives us 3/4, and so on and so forth. An example of an increasing exponential function, so such as that 2 to the x or 3 to the x that we practiced with, is the speed of a rocket increasing. So the initial blast causes the rocket to start very slowly. You kind of imagine this when the rocket starts to take off. It starts very slowly as it gets off the ground. But the speed increases exponentially. After that first few moments, it starts to really take off and get quicker and quicker. How does this differ? So a linear function has a constant rate of change. So an example of this would be a person walking at a constant speed. So if a person is walking at 2 miles an hour for 5 hours, we know that 2 times 5 would mean that they would walk 10 miles in that 5 hours. So some common mistakes. So we can write negative signs 2 different ways. So if we put -3 inside parentheses with that power to the x on the outside, we get all these really weird points. So if we were to put a line on this, it would swoop down and then swoop up, then swoop down and swoop up even farther and follow that pattern. And it would be a really wild graph. And this we can recognize by plugging points into our table. So -2 gives us 1/4 or 0.25. -1 gives us -1/2 or 0.5, -0.5. 0 gives us 1. 1 gives us -2. And 2 gives us 4. So this kind of follows that wild up and down pattern that I was talking about. Now, if we put the whole equation in parentheses with the negative outside of the parentheses, that works. It just flips the graph upside down, similar to how we would flip a parabola upside down. So for that 2x, we can just flip put a negative sign in front of all these values. So instead of just having 1/4, 1/2, 1, 2, and 4, we now get -1/4, -1/2, -1, -2, and -4 for our y values. Some other common mistakes. 1 to the x. Anything that has a base of 1 that's a power is always going to be 1. So this just gives us a flat line that is always at 1. Another common mistake is accidentally writing, instead of b to the power of x, where b is an integer, writing x to the power of b. X to the power of b would be something like a quadratic function, a cubic function, depending on what that b is. But b to the x is always going to be an exponential function, because the exponent for exponential functions are always variables. The exponent for quadratic functions are always integers. And quadratic function case, that integer is 2. Cubic function case, that integer is 3. So finally, an exit ticket. I want you guys to pull out a piece of paper and try out these problems. I will give them a grade overnight and turn them back into you guys tomorrow. That way I can better judge what you guys picked up from today's lesson. We'll also go deeper into that ball dropping problem. So firstly, determine if the functions are quadratic, linear, or exponential. Remember, quadratic is going to have a power of 2. Linear is just going to have an x, and exponential functions are going to have that power of x. So we have y equals x squared, y equals 2x, and y equals e to the power of x. An important note, e is a number, not a variable. Secondly, determine if the following exponential functions are increasing, decreasing, or constant. Y equals 3 to the power of x, y equals 1/3 to the power of x, and y equals negative on the outside, parentheses 1 to the power of x. So I'll repeat that last one. Y equals parentheses 1 to the power of x with a negative sign outside of that parentheses. So we wouldn't have a wild graph. It would just be a flipped graph. And then finally, make a table and a graph of y equals 5 to the power of x. So just go ahead and do x values from -2 to 2 and give that a graph. Point those points on the graph and do a line of best fit. Good luck with that, you guys, and have a good rest of the night.